Hi, everybody. I'm glad you joined to my talk, which is accelerating Suricata with DPDK Prefilters. My name is Lukáš, Šišmiš, and here is a little agenda. That's what's ahead of us. There will be short introduction to packet acquisition modules of Suricata. Then we will proceed to experiments with DPDK capture method. And then I will present concepts of DPDK Prefilter and DPDK Proxy. So to say a few words about myself, I'm a researcher at CESNET and at the same time the PhD student at Brno University of Technology, which is located somewhere where the pinpoint head is. I work at CESNET, which does tools for network monitoring and security, high speed and network traffic analysis, and DDoS mitigation and detection. Now, to get more deeply into what's ahead of us, we will briefly go through the Circada architecture. Suricata consists of 4 modules, as we can see on the right. There is a capture, decode, detect, and output modules. And each module consumes some of the resources that the server has. So, and if we optimize one of these modules, then the whole Suricata can be faster, be more performant, and increase in packet processing in general. So we try to focus on the capture method or packet acquisition modules. And to give you a little idea what's inside the packet acquisition modules, you can see the image on the right. There is quite complicated path how a packet gets from the NIC to Suricata, but we don't need to go too much into detail. It goes through the kernel space where Suricata at the end Suricata capture method or module receives the packet and moves it to Suricata itself. Suricata contains multiple packet acquisition modules like AF packet, NFQ, or PF ring, or some others. Generally speaking, it provides some kind of interface between the network libraries, as mentioned, and Suricata itself. So it receives packets from these libraries. Individual modules vary in performance, so that means some of the mentioned modules can be faster than others. Now we try to, we implemented the DPDK capture method or module. DPDK stands for Data Plane Development Kit, which is generally another network library or set of data plane libraries and a network interface controller. But what's different in DPDK is that it bypasses the kernel space and the packets go directly from the NIC to the application. This enables to have the packet processing faster and saves some resources and for other modules. As you have might seen in the previous slide, there is interrupt handler. So the packets from the previous slide are handled without interrupts, but in DPDK packets are received with polling, which means the application constantly asks NIC if there are any new packets. DPDK is an open source project under Linux Foundation, and as it's quite a big project, it received support from many vendors like Intel, Xilinx, or Mellanox. So, and since since this provides a quite standardized approach how we can interact with the NICs. And also, some of these vendors support special hardware offloads in their NICs as well. DPDK as a data plane support also virtual interfaces and virtual environments in general, like Docker. So it can be very interesting to see this capture method in cloud environments as well. Now I'll skip the part where I implemented the module, but I would like to rather present you the results of the module by itself. It was implemented using the standard packet acquisition API that Suricata provides for these kind of modules. Currently, it supports worker run mode and works both in IPS and IDS mode. So both modes are supported. And the initial contribution currently, which is in the pull request, limits the scope of the features that it includes. So currently, it's focused on rather supporting the physical NICs running on physical servers. And the minimum DPDK required to run the Suricata with DPDK is 1911 or newer ones. Before I'll show you the results of the experiments, here is the experimental setup, and then in the next slide will be the test bed of how servers were connected. Now, the DPDK capture interface was tested against a tuned AF packet to give some baseline for the tests. And both of these interfaces were run in worker run mode with NIC queues mapped to the threads in a 1-to-1 ratio. So each NIC queue had one thread binded with it. And it ran in IDS mode. It had enabled ET rules, ET open or emerging threads open, which contain about 21,000 rules. Now the machine that Suricata ran on had CentOS installed, had 10 physical cores, 64 gigs of RAM, but it was based on one node, and I used Mellanox NIC for the testing. Here is the test bed. My laptop was a control station that issued commands to Suricata server and the replicator server. Suricata server was, the server contained only Suricata. The replicator server contained a PCAP that was sent over the network with a replicator card that the replicated traffic from the PCAP to have more flows and bigger traffic than it was originally captured. The control station then grabbed the results from both machines and logged it into the results. Now we are moving to experiments, or the results of experiments. We can see a graph that contains two axes, X and Y axis. X axis describes transmit speed from the server that transmitted the traffic, and the Y axis describes dropped packets, which was calculated as number of sent packets minus number of received packets, and this was then divided by number of sent packets, so the usual equation for dropped packets. And we can see two lines, which, as previously mentioned, what is line for AF packet capture interface and DPDK capture interface. The AF packet capture interface is the blue line, and the DPDK is the orange line. Now we can see that DPDK processes packets at speed of something like 6 gigabits per second, while DPDK starts to drop packets at the speed at something like 2.5 to 3 megabits per second. I'm sorry, 2.5 to 3 gigabits per second. Now, if some of you notice that these speeds are quite high, it's important to notice that these results are measured with no rules enabled. And these rules are, and these experiments were done on one NICU as is shown in the description. One NICU, as previously mentioned, is binded with one thread, so only one thread was enabled within these experiments. And so the DPDK doubled the performance of AF packet in this case, with more queues or more threads enabled, and again with no rules enabled, we are getting to higher speeds. And similarly, we can see that DPDK is able to process more packets than the AF packet capture interface. Now, it was nice to have measurements without rules, but it's also important to measure the performance of the Suricata with rules. Now we have here in this graph rules enabled, as previously mentioned, so the rules from ET open, and it works on one NICU. So on one thread. Here, the AF packet reaches speed of about 600 megabits per second, and after that, it starts to lose some packets, while DPDK is able to receive up to 700 megabits per second, which is about 16% increase in performance. But this can vary very much on how many rules are enabled. If we enable less rules, the gap between these two interfaces will be bigger, and on the other hand, if there are more rules, the detect module will be more resource hungry and will eat up more of the precious resources, and there will be less resources left for the packet capture module. So in this case, it provided about 16% increase in performance, with more queues enabled and more threads enabled. It provides similar results as in the previous graph. It was able to receive more packets. DPDK didn't lost almost any packet at 6 gigabits per second, while AF packet already lost some. So, but it continues in the trend from the previous graph that it still can receive more packets. So it was the implementation of DPDK capture method was can be considered as a benefit. It can benefit in more, or it can process packets at higher speeds. We could see the massive performance increase with no rules enabled, while some increase in performance with rules enabled. It was able to help Suricata with packet processing. Now, implementation of packet processing was or packet capture module was one thing, but we need to rather focus on ways how to pre-filter the traffic, how to help Suricata to not inspect all the traffic. And some of you already know that there are techniques for this. One of the most well-known are the bypass or flow shunting, which are both really good techniques, but still Suricata needs to tell the network library that I'm not interested in this traffic anymore, or something like that. And but we also thought that it can be interesting to have something in front of Suricata that can tell that this traffic is safe, so it doesn't even need to go to Suricata. That's the concept of DPDK prefilters. Now, DPDK prefilters, as we can see, it implements a bypass functionality. If we move to the slide, to the previous slide, we can see that a DPDK prefilter is in front of Suricata and is connected to the NIC. It receives packet from the NIC, and then the prefilter sends the packet to Suricata. Suricata decides to tell the prefilter that it doesn't need to see the packets anymore, or this flow doesn't need to see the flow anymore. Then the prefilter will bypass the traffic. But this use case is something that's already there. It kind of resembles the XDP bypass or something like that. But in the prefilter, there can be an advanced prefiltering, which might include that the NIC sends packet to the prefilter, but with that packet, it also sends a NIC meta information. That meta information is basically generated and processed with the NIC, and the prefilter can look at these meta information from the NIC, process them even more, or maybe pre-filter them, and append a pre-filter meta information to the packet before it is sent to Suricata. Now, Suricata can then look at these meta information, and it can help Suricata with the detection of packet processing, to basically decide faster, according to these meta information, what to do with the packet. Now, this can help Suricata, but as we can see, on the transmit in the transmit direction from Suricata to DPDK prefilters, Suricata can also append meta information to the packet and before it is sent to the DPDK prefilter. That can be for use cases when there is, for example, a machine learning model in the DPDK prefilter that can receive this very precious information from Suricata to learn by itself. Then with the advanced pre-filtering, if the classifier or the machine learning model in the DPDK prefilter is good enough, then it can directly do the decision instead of Suricata and and therefore it doesn't need to send those packets to Suricata, but the decision can be made directly in the prefilter. Now, with the DPDK prefilters, we can see that there is a NIC meta information. The meta information basically depends on hardware offloads of the individual NICs. This meta information depends on what hardware offloads we have in the NICs, and then they are sent to the prefilter. But prefilter can also be a special place where vendors of the NICs can try new prototypes of hardware offloads, because it's separated from the Suricata, but the prototypes are not hard to implement because they are in software. And if the vendor sees that the prefilter or the prototypes pays out, then the prefilter can be implemented into the NIC itself, where it can help even more. So it can, in the DPDK prefilter by itself can even serve as a platform for quick prototyping of hardware functions. Now, in this slide, I've described in this slide at the diagram, and I would move to the DPDK Proxy. DPDK Proxy builds on the concept of DPDK prefilter, and kind of tries to enhance it in some ways. DPDK Proxy can be very useful when we have multiple applications and let's say multiple network analyzers, and we want to run them on one server at the same time, side by side, on that we want to inspect with them the same traffic, possibly from one network card. Now we can look at the diagram. These apps can be, as mentioned, side by side and connected to the DPDK proxy. The DPDK proxy then receives packets from the NIC and distributes these packets to the applications. What's important to note that it can somehow classify the traffic. It can differ, let's say, between encrypted and unencrypted traffic, or maybe other profiles of traffic. And secondary applications or the subscribed applications can define in what traffic they are interested into. We might have a network analyzer that's not interested in encrypted traffic, so the proxy will be only sending unencrypted traffic to this application. If we move on the description on the slide before, so it can split the traffic between multiple apps, but at the same time it can share the same packets between multiple applications because they will be stored in one mempool from where they will be accessed by multiple applications. And similarly to the prefilter and other techniques mentioned before, it provides a bypass functionality. So if the unencrypted traffic analyzer will not be interested in certain flow, it can also tell it's the DPDK proxy, and this flow will be also omitted or bypassed for the given application. as we can see, between the applications, there is inter-process communication, which would be a way how the subscribed applications would communicate with the primary application on DPDK Proxy, just to create new ways how to connect to the DPDK Proxy. And as you can see, the 3 dots on the very right, it means that there can be not only 2 applications but multiple applications. It depends on the configuration of the DPDK proxy. Now, this would be all for the DPDK proxy concept. And if we move to the conclusion or the final wrap up, it was during the recent months, it was possible to implement a new packet capture method based on DPDK. It doubled the performance of the packet reception with no rules enabled compared to AF packet, while it also increased by 16% the performance of Suricata with ET open rules enabled. And maybe from my point of view, it created opportunities for new possibilities with DPDK library. This, as I mentioned, this can be used for the DPDK Prefilter or DPDK Proxy, but it also can be used in cloud environments to support DPDK capture method in virtual environments. Or there are also other interesting techniques in DPDK, how to even further accelerate the Suricata using the DPDK. Now, the DPDK prefilter is designed for an advanced prefiltering of packets to kind of also accelerate the Suricata and make use of hardware offloads, possibly, but it can also serve for fast hardware prototyping because it's a separate application from Suricata. So it defines clear boundaries between the prefilter and Suricata by itself. And then the final concept, DPDK Proxy, provides a possibility to inspect the traffic by multiple applications on one server, while these applications run side by side, and therefore it can utilize the resources of the servers and even more. Now, this would be all from me, and I'm happy to answer your questions. Thank you.